Okay, just to introduce myself, this is Chaitanya. I'm currently the head of acoustic group at Institute of Sound and Vibration Research, University of Southampton. And as you all know, today's the speaker is Franck Bertagnolio, who has an extensive work done on wind turbine noise, especially from last 28, 30 years. And especially his work is more focused on developing engineering models for wind turbine noise, understanding the noise sources, and try to also go on field and to get some acoustic measurements on wind energy. And also did some work on CFD of the elasticity problems on wind turbine blades as well. But from last for many years, his expertise lies on wind turbine noise modeling. So, and in today's presentation, we'll be talking about the low frequency noise in wind energy. Thanks a lot, Frank, for agreeing to speak with us. And over to you, Frank.
Thank you. Can you see my screen or the slides?
Yes, we can see.
Okay, but yeah, thank you for your introduction and thank you for inviting me to this seminar. And I will be speaking about low frequency noise in the context of wind turbine and wind energy. So yeah, I will define what we are speaking about. When we speak about low frequency noise, it includes infrasound. I will go over some aspects which are not so engineering related, like perception, impact assessment, and regulations. And then I will go more into the generation of these noise sources for wind turbine, look at different mechanisms, and then going to modeling aspects and focusing mainly on what we do here at DTU, but other methods as well, which has been used in the literature earlier. And this will not be necessarily this, in a chronological manner. But yeah, why should we care? First, there are some issues, of course, when we speak about noise, it's about neighbors and how they perceive the wind turbines. When we speak about low frequency and infrasounds, it cannot really be heard mostly. We'll see how and when. And therefore, there are some mystics around it, and it makes people nervous, and they don't really like wind turbines sometimes just because of that. But they still, there are some studies about their actual impact, and we'll come back to that. Our general knowledge, we know that it's from wind turbines, the noise levels are quite small and comparable to what other industrial noise sources or even the background noise equivalent to these ones, but it's still measurable. So it definitely is worth studying. And again, there are relatively few studies on the impact and on the modeling part as well. Although it start to emerge in as it is a problem, at least in some countries. So just to be clear, low frequency noise, when we speak about infrasound, it's usually from 0.1. It's very arbitrary. At 0.1, it's like 10 seconds. So it might be just a change in pressure, and it could be, I'm not sure if it could be defined in noise, but infrasound is up to 20 Hertz usually. And then low frequency noise is from 20 to 200 Hertz. Sometimes 160, depending on the authors. And generally, we refer to low frequency noise for everything below 200 Hertz, say. So there is not a clear definition here, but we know the range of frequencies. Then there is a question of audibility, and here you have three figures. It's basically the same. On the x-axis, you have the frequency, and here on the left, you have different. It's measuring phone is basically a noise level that you hear, and the threshold is basically the noise level that you need in decibels to hear this sound. And you see that going to low frequencies, and you need very high or higher and higher levels so that the sound can be audible. And there have been a lot of studies on that, and I'm just here taking an old one from 72. And then here you see that, so on the top, it's different method of measuring this threshold, and on the bottom is different articles. So you can see it converge. The tendency is clear, is that yeah, the lower the frequency, the more energy you need to be able to hear it. So that's that's a fact. That's what we don't really hear at some low frequency noise. It's not always audible. Now, if we compare wind turbine noise to other noise sources, here it's compared to road traffic noise, and it's a study from Carl Bolin from KTH. It's from 2011. I'm a bit surprised here that this curves in the spectra in color, they are for wind turbine at 0.5 and 1 kilometer, and small turbine and large turbine, but still they more or less coalesce. It's, but you still see that it's usually, well, it depends on where you are, of course, but in their study, it's always lower than road traffic noise, actually. And when you go, and then if you superpose the audibilities, then you can see that below 30 hertz, everything is not audible, actually. So that's more or less common knowledge. And there is one more important part about low frequency noise, is that here you have frequency again on the bottom, and here is the absorption, atmospheric absorption by the air. So at different temperatures here, but you can see when you go to low frequency, this atmospheric absorption is very low or getting very low. And that means that low frequency noise will travel over large distances. So that's another fact to account for when you consider this issue of low frequency noise. So, and the last thing is that, if it cannot be heard at very low frequency, like infrasound, it can be felt by the body, by your body fluid or your chest cavity, or and then it can have a possible impact on health, and it's not really clear, and I will come back to that a bit later. Here I will go very fast, but you have a lot. Well, all these facts create a lot of debates and doubts, because there are quite a few unknowns on this low frequency noise and impact, and you have, I just pick up a few one, but you have a lot of articles, and some scientific, some less, with rarely answering the question to the bottom, solving the problem to the bottom. There have been some actual impact studies, and I know 4 of them. I think that's the most recent one and the most complete one. One in Canada, one in Finland, one in Germany, and in Australia. And you can see for the 4 of them, these were commissioned by the government itself. So they hired some independent companies to do the research. And I think the main conclusion from all of them that there was not real impact from low frequency noise on neighbors. I will take Denmark as an example. What happened with the low frequency noise across the years? I will go fast, but I can't understand myself that low frequency noise has been a problem in Denmark. It has been discussed a lot, and I would like to make the parallel with the amplitude modulation. I guess you have heard of that if you follow a little bit what's happening with the wind industry. But amplitude modulation has been a big issue in the UK, and I'm pretty sure that what I will explain now is more or less what happened as well in the UK. But it started very early in Denmark, because they were one of the first to implement this large-scale wind industry. And then they were starting to have some complaints, and then some research were done, but they use A-weighted, and then people start to complain that it was not reflecting low frequency noise. Then the media start to come in, And then a lot of people, there was a lot of discussion on the internet and so forth. And that's where really the problem become alive. Then in 2011, there was a milestone with the government implemented some noise regulation, including the low frequency noise. And for this, they define a metric, which is a LP-A-weighted low frequency. So it's basically an A-weighted spectrum, but it's limited from 10 to 160 Hertz. So you just take that frequency band and you can integrate it, and you get a metric for the low frequency noise. And it should be less than 20 dB inside houses. But still, people were not, well, there was still some debate, even though this metric or this regulation was respected. There was some debate, and there was a study which didn't find any actually correlation between low frequency noise and health effects. But it continued on and on. It's still a debate today, less than it used to be, but it's still, people are still complaining about it. I will stop with that with this perception effect aspects. One last thing, you may find things that offshore wind farms are not subjected to noise problems, but actually they are. And there's two parts here. Is that when you have a wind turbine at sea, well, as I said, the low frequency is traveling over large distances. It's probably attenuated by the atmospheric absorption. And then in the Danish regulation, in the models, you have to include this multiple reflection, which when you have the favorable wind condition, then the wind, the sound will bounce on the earth surface, which is the sea floor or the sea surface, and it has to be accounted when you calculate the noise at the receptor. The trick here is that actually you have to add this to the existing wind turbine already existing onshore. And if you take this regulation to the letter, it proves actually you cannot install any more offshore wind farm in Denmark, actually. So actually now there is some studies to how we can change that, and well, that's the plan at least. But still, offshore wind farms are subjected to noise issues. Now another aspect, how to measure it. It's not easy. Here you have an array. That's more for infrasound. That was used to detect nuclear detonation, maybe on the other side of the planet, but it's still detectable. That proves that it's traveled quite well. More related to wind turbine, so there were some studies from Belgium where they try to measure at very low frequency from a wind turbine, and they had to design their secondary windscreen quite large. Otherwise, you might have measurements which are drawn in background noise actually. So it's not easy to measure as soon as you go to very low frequency. In the field, not in an anechoic environment in a laboratory. Last thing, then in Denmark we have regulation on low frequency noise, and it's indoor levels. And here you can see the difference between indoor and outdoors, and it's up to when you go it's 10, of the order of 10 to 20 dB. So basically, and here the different curves are for different house types. Actually what you measure inside will be different depending on your house. So it's quite difficult to again assess the noise levels or predict them. But let's now come to the actual problem of wind turbine noise. Now we'll go more into details. I suppose many of you have seen this picture if you are interested in wind turbine noise from Elements from Netherlands. So which was taken with a microphone array, which is located here. Actually, you can see on the picture, and it's an average of the noise emission from the turbine. And you can clearly see that at the center you have noise emission from the nacelle, and this is mechanical noise, so it can be generated by several components, but mainly the rotating one. like the gears, maybe generator, and then you have cooling fan as well, which can generate noise. And all of them are tonal in nature. And then on the towards the tip of the airfoil, which is traveling the fastest across the air, you have aerodynamic noise, which is usually broadband. But we see that in the context of low frequency noise, it can be tonal because it will be associated to the bed passage frequency when it hits the tower. Not hits, but yeah, passed by the tower. Yeah, both of them can generate low frequency noise. I mean, mechanical noise and aerodyc noise can generate low frequency noise and infrasound. In the case of mechanical noise, it has been mostly solved and by using damping and nacelle insulation. I'm not saying that it's completely solved. It's just that they've done a lot to reduce these noise sources. And today it's considered that aerodynamic noise is dominating for a modern wind turbine. Here, this is illustrated with this calculation. It's a model, but on this plot, so you have a frequency spectrum from a model for a wind turbine. What you see here in pink, this is trailing edge noise. So generally that at the trailing edge from the boundary layer developing on the airfoil. And you can see it's dominant. Yeah, actually it's quite low here, but it's usually dominant around 1000 Hertz. Or yeah, I guess it's a small turbine here was used, but so it's dominating in the higher frequency range, and the black dot are the turbulent inflow noise. I will come back to that, but that's the one dominating at low frequency. So that's really what we want to focus on, this turbulent inflow noise or ingestion noise. You have other noise source mechanism, but maybe one worth mentioning is stall noise, which will possibly produce as well rather low frequency noise, although it's not clear. The stall noise occurs when the turbine is not operating optimally, so it's like more like a dynamic problem, and it's still a topic of research. So yeah, what do we speak about when we speak about turbulent inflow noise or ingestion noise, or sometimes leading edge noise as opposed to trailing edge noise? Is actually the interaction of the blade, the rotating blade, when they pass through the atmospheric turbulence. And then here, the mechanism is quite well understood. So if you have an airfoil you create lifts, okay, and lift is pressure. And this lift is proportional to the relative wind speed here in black, as well as the angle of attack. But if you have atmosphere, you have a varying wind speed, you will have a varying angle of attack, and for aerodynamicists, it's obviously creating some change of lift. And when you have a change of lift, it's a pressure exerted on the airfoil, and if you have a change of pressure, then you have acoustic wave. It depends again at which frequency, but that's the basic principle, and it's really what creates low frequency noise. Now you have as well a tower, and when your blade is passing during this downward motion, it will pass near the tower, and the tower will deform the floor with a reduction of the wind speed, incoming wind speed. And again, you will have a change in wind speed, change in angle of attack, change in lift, change in pressure forces. It will also as well create acoustic wave. And here again, in the low frequency range. That's what is called blade tower interaction. And I will come back to that several times here. Now, if I go back in history for the studies, actually the first large studies about wind turbine noise and low frequency noise was done by NASA. They had this program after it started in '74 after the first oil crisis. So they started to investigate wind energy for their electricity supply. And there's this very long program which spanned, so they started with a small turbine of 200 kilowatt, and they plan actually to go to 7.3 megawatt. Actually, in practice, they didn't build this one. They stopped the program before, but they still went up to 4 megawatt. And you can see this, yeah, 3 of these turbines were downwind turbines. That is, the rotor is downwind of the tower, and 2 of them were upwind. And actually, I will concentrate on this one, which is called mode 1. It was a downwind turbine, 2 MW. And you have a picture here, 2-bladed. But one noticeable thing is that they are all 2-bladed, actually. It's not like the Danish concept, 3-bladed. They thought it was cheaper for the story. But yeah, they have this turbine, which is downwind, and you have a massive tower here. And since now the blade is passing in downstream of the tower, it's passing in its wake. And again, here you will have a larger wind deficit because of the tower wake. And it will be the same, change in wind speed, change in pressure forces, acoustic wave. And actually this turbine, this mode 2 turbine, created a lot of problem, or yeah, it was problematic for the neighbors because it was generating this very uncomfortable sound wave at low frequencies. So they started to investigate this with analytically, or with a model, and it's called Viterna model, and it's based on the superposition of the blade passage frequency harmonics, and it's just using the force and the torque as an input, the time series of the force and torque. Decompose it in harmonics, and they arrive to some noise levels. And then they created a code which takes all the parameters of the turbine and all the necessary parameters to arrive to a sound spectrum. And what they get, here you have the measured data, which are the points, and their model, which is the lines. So it's not exactly matching the measurements, but it's still, at least pretty close in terms of levels. The other thing that they could measure actually is the directivity around it. So here you are on the top, looking at the turbine from the top, and here you are on the, like if you have a microphone on the ground, and you can see that it has kind of a dipole directivity type. So you have less noise when you are in the rotor plane. That's what is well known today, actually not only for low frequency noise, but as well for trailing edge noise and all. If we use this model to compare a downwind turbine versus an upwind turbine with the same rotor, but just put upwind and downwind, you can clearly see that the upwind turbine creates less noise. Here it's an integrated noise spectra from 20 to 50 Hertz, and here you have the distance on the x-axis from the turbine. But clearly, the downwind turbine is much more louder. And then they improve the model to this mode 2, 2.5 megawatt here. And that was a Lawson model. And he had another approach, but he used basically ambient model, if you know, I will come back to that, ambient model for the turbine inflow noise, which is a more advanced model for predicting it. And I will explain what is ambient model. And they had BPM model for the trailing edge. And they pretty much match the what was measured in the field for this mode 2 turbine. So ambient model, what it is? Well, it is a geometric simplification of the airfoil. Basically, you consider it as a flat plate, and you look at a monochromatic wave, incoming wave, and then if you assume that your airfoil is infinite towards the trailing edge, then you have an analytical solution for the pressure. You can end up with knowing the pressure on the surface, and from there you use curl, and you arrive to a noise spectrum. And here you recover the incoming turbulence spectrum, and here transfer function. I must say that this transfer function is associated to scattering effect, so it's to higher frequency. In the low frequency, it just should behave like a dipole, basically. So now what we do here at DTU, we are using a similar approach than Lawson actually, but with more advanced models. Although we still use ambient for the turbine inflow noise. And we do that in the frequency domain. we have a BEM code, which is a code to calculate the airflow around a turbine rotor. So it gives you access to the relative velocity, induction velocity, angle of attack, and a lot of things that we need for inputting in the models. And then from this, we discretize the blade, calculate the noise for each blade section, integrate, and get a far-field noise spectrum. And again, here we use some trailing edge noise models, better than BPM or more advanced, but still the ambient model for the turbulent influence. And what you can see here, we have been calculating for that's a 2.3 megawatt turbine. And you clearly see again here that the trailing edge noise is dominating in the high frequency range, and again, the turbulent inflow noise is dominating in the low frequency range. And that's what we saw earlier. And on the left, it's non-A-weighted. On the right, it's A-weighted, which decreased because of this audibility. That's why therefore this A-weighting is decreasing the noise level according to our human hearing. I will pass this one. Now we have another version of the code. So it's exactly the same code for the aerodynamic, but at the airfoil level, we compute in the time domain. And this time we take into account the actual mechanism of the angle of attack variation that you can get from this BEM approach. And we calculate from this the lift variation and the acoustic wave. And to do that, we use what is Fox-Wheeler-Hawking, but the solution is called Farasat formation 1A. And we only keep actually the lift part. We know that for wind turbine application, all the other parts are neglectable. But basically give you the noise in the far field as a function of the variation of the lift on the airfoil, or the pressure on the airfoil. It's very similar to Curl's approximation, but yeah, it can just take into account a moving object. So we can do this calculation with some, for example, inflow turbulence. We get a time series of the noise. We can do FFT, and we can calculate a spectrum here. And then if you focus on the very low frequency part, you recover the bed passage frequency, which in this case is 0.4 Hertz. And of course, when you change the window of your FFT, you can get a more smooth spectrum. So what we have done, we try to see if it's important to take into account the actual lift distribution or the pressure distribution, except of using the one single component, which is a lift, which is the integrated pressure forces. And we see that actually it doesn't make a big difference. There may be 1 dB difference, but so it's much faster to use a single lift force in this Farasat solution. So that's what we do. Then we try to change. So we have some incoming turbulence here, and we can control that in our model. And we change from 1 to 10%. And as you can expect, you have a huge increase in noise levels from the left to the right. Now in this Octo model, our BEM model, we can include on top of the atmospheric turbulence, we can actually include an upwind turbine and its wake. And then we can see, we can have the upwind turbine or the downwind turbine be in full wake, that is their axis is fully aligned, or it could be in half wake. So basically you have only the half of the rotor plane, which is intersecting the upstream turbine. And we can do some calculation. Again, it's pretty straightforward. And we see if we have low turbulence intensity, then actually no wake is in red here. But if you have wake, then you have a huge increase in noise levels. Surprisingly, it doesn't make a big difference if it's half or full wake. But if we have 10% intensity, then actually it seems that the wake has the same effect as the turbulence intensity is not so important anymore. Then we compare our model with the Viterna model. And here I will just say that we recover more or less the Viterna is with the crosses, and for the same turbulence intensity we have the green curve, without crosses, which is our model. So it fits relatively well, not so much in the infrasound part. And here we had some measurements of a turbine. Yeah, it's not fitting very well, but we didn't have many information. We didn't even know what was the turbulence intensity for this measurement, so it's pretty difficult. And here you have a peak. It's probably some probably mechanical noise. I would expect probably some tonal noise. I don't know. Now, if we look at the downwind turbine, you have turbulence actually as well in the wake. And what you can do is to do CFD of this, calculate this flow with DES to make it relatively simple. So that's what we did. We do the DS simulation of the rotor, of the tower. We store that in time, so it's quite expensive. So to do that, we we inject that in the Arc2 simulation. So you just assume that there is no feedback of the airfoil on the wake, and basically the blade will cross this turbulent flow field. Yeah, for the storage, we just use a coarse grid to limit the memory storage and single precision. That's the trick to make it affordable. And what you can see here is that here on the bottom, you don't have this turbulence, but if you add this turbulence, actually, so that's for different wind speed, but you can see that actually it will contribute for a downwind turbine significantly to the noise level. Now, if I come back to an upwind turbine and the blade tower interaction, so we saw that when it's passing in front of the tower, the airfoil will emit noise by the change of lift. But it's an interaction. What about the tower? It will have some. There will be some pressure changes on the tower surface itself. And actually, there are two studies. One from Australia, Jovenas, and one from Germany, with Klein. Both used some 3D CFD calculation, and they showed actually that the tower is radiating more than the airfoil itself. So we decided to investigate that, and we again use our model, and I will show how it is set up. It's a very simplified model. We just assume that the airfoil is actually traveling on a line, horizontal line, parallel to the ground. So we just project the actual blade position to this line for each radius of the rotor of the blade, and then it's moving. And actually, when the interaction is maximal, that's where this assumption is the best. So actually, we believe that it's a relatively good assumption for a model like that. Now we model our airfoil as a vortex. So basically, here in a 2D plane, you have the tower, and you have a moving vortex. And from there, we use 2D potential theory. So you can calculate the mean flow and the flow from the vortex, both interacting with the tower, which is in a cylinder in 2D, and you have an analytical solution for that. Here you make the assumption the flow is quasi-steady, but you recover the unsteadiness by using Bernoulli, which allows you to actually calculate the pressure on the tower. And again, we use Farasat, as we used earlier, to calculate the far field noise emitted by the tower. Again, this is implemented in our BEM code. And we here compare the results for an NREL 5 megawatt turbine, and we'll be comparing with the LES calculation from Germany. So it's exactly the same configuration, just two different models. So that's their results. So you have a spectra here, and again, it's tonal because it's associated to the blade passage frequency. And here you can see, so here you have the rotor. A is downwind of the rotor on the ground. And you can see here that the tower, which is a blue dot, is higher than the rotor emission. Actually, in our case, it's not, they're actually quite equivalent. They are not, yeah, we don't have these clear differences. And here the rotor is slightly higher. And you might ask why, when you consider the red is the summation of both, and in our case it's lower. And here it's because there is some, I didn't check, but I'm pretty sure there are some destructive interferences where, at this point at least. But if we look at a point which is on the rotor plane, then that's what we find, that actually the tower is rotating most in our case, and it's the case as well in the LES calculation, I think. Actually, no, here they are equivalent. So yeah, there are some differences. We look at directivity. So on the left, you have here's the rotor, again with this noise dip in the plane, transversal plane. And then you have the tower, which is much more monopole-like. And then when you sum up the two, you have this one. And here I'm comparing with the measurement. No, so that's Uran's calculation from this group in Australia, and we recover basically the same, at least the same dipole-like emission directivity for the rotor, and a more monopole-like for the tower. Here the tower is in red, and yeah, the combination is in black. Yep, that will conclude my talk. So yeah, low frequency noise and infrasound has been, at least in Denmark, a serious concern for neighbors and citizens, and there has been a lot of debate. We saw that in the beginning. And this arose with growing turbine size back in at the start of the industry, but now we see that they are growing even bigger, and it might become even more important problem to address, both for regulation, but as well for having models to be able to predict these noise occurrences. We saw a few models. I didn't go so much into high fidelity like they do in Germany. I concentrated on more analytical models. The thing that we hope that, for example, with the model I present, we can have a solution within a few minutes on a PC. Well, when you do LES of a full turbine, that's quite costly. And then, we don't have, well, first, we have to validate our models. They are not fully validated. We see that there were quite some discrepancies with the LES, but we have a crucial lack of experimental data. It's very difficult to get at least the manufacturer to share their data, and it's costly to go in the field and do it yourself. And you need to know how the turbine operates, which is as well something the manufacturer don't share. So thank you. That will be it.
Thanks a lot, Frank. That's really informative. A lot more new things I learned. So we have like 15 minutes for questions now. I mean, please, if you have any questions, so please. So there's one question from Konwani. Why are you